top K frequent elements with approximate counts using sketches. Problem constraints first, then the plan, and then the deep dive. We process up to 10 to the 7 integers. Memory is at most 256 megabytes. We must return top K frequent elements with approximate counts within plus or minus 1%. The approach must be streaming, single pass, and sketch-based. The high-level plan is a 3-block pipeline. Stream items enter a sketch that maintains approximate counts. A small top K data structure keeps candidate heavy hitters. At the end, we query the sketch for their counts and report the top K. Count min sketch gives an overestimate with additive error epsilon times n, with failure probability delta. Width W equals E over epsilon. Depth D equals natural log of 1 over delta. For 1% error, epsilon equals 0.01. Width is about 272. With delta 1 over a million, depth is about 14. Memory equals W times D times counter size. We draw a compact count min sketch with 4 rows and 16 columns. Each row uses an independent hash function. Updates add 1 to 1 cell per row. Items arrive at the sketch one by one. For each item, we compute 4 hash positions, 1 per row, and increment those counters. To estimate the frequency of an item, take the minimum of its 4 counters. The estimate is never less than the true count, and at most epsilon times n above it with high probability. With 1% error, we choose width around 272. With failure probability 1 over a million, we choose depth around 14. Using 4-byte counters, the table takes about 15 kilobytes. The memory budget easily fits within 256 megabytes. To keep candidates, we use the space-saving heavy hitter structure. Maintain M counters of items and estimated counts. On seeing an item already tracked, increase its counter by 1. Otherwise, if there is space, insert it with count 1. Else, replace the minimum counter item with the new item and add 1 to that counter. This achieves additive error at most n over m for every reported item. The combined method is straightforward. Use space saving of size m around 1 over epsilon for 1%, that is 100. At the end, extract all tracked items as candidates. For each candidate, query the count min sketch using the minimum of its row counters. Finally, sort candidates by these estimates and return the top K elements. Count min sketch over estimates because collisions only add false counts. The expected overcount is bounded by epsilon times n, and the probability of exceeding that bound is at most delta. Depth reduces failure probability via independent rows, and the minimum operator. Width reduces collision rate in each row. A concise end-to-end example. Suppose the top K structure holds x1, x2, and x3. We query the sketch and obtain estimates 8, 5, and 4, then sort and report x1 first. Complexity. Update time is O of depth, that is about 14 hash evaluations and increments per item. Query time is also O of depth. Memory for the sketch is width times depth times counter bytes. Add the space-saving memory, which is O of m, with m at least 1 over epsilon. Guarantees. Counts overestimate by at most epsilon times n, with probability at least 1 minus delta. Reported top K are correct up to this additive tolerance with extremely high probability. This is how to compute top K frequent elements on massive streams under strict memory. using CountMin Sketch plus space saving, needing 1% accuracy and high confidence.